Hi students, all of you welcome. Welcome to Sunil Engineering Academy. I am Sunil Kumar Bandar. Students, in this power systems through topic wise MCQs, we have already completed 8 sessions. It is the ninth one. Okay. And students, if you want electrical engineering PDFs, you can visit sunilengineeringacademy.com. In that, you can get all the PDF notes. You can download from that. Okay. And you can also join in this Telegram group. So up to cables we have completed na. Sorry, up to corona topic we have completed. We need to start a cables topic. Okay, cables and insulators. So in this session we are going to practice all the questions belongs to underground cables and also insulators. Okay. Yes. Let us take the first question. Cables are used for underground services from 33 kilovolt to 66 kilovolt is categorized as dash. Low tension, high tension, super tension, and extra high tension. Okay. Here this classification question is very important, belongs to underground cables. So let us take a small note on this. Okay. So low tension, LT. Low tension cables, we can call it as LT cable. Okay, so it is 0 to 1 kilovolt, 0 to 1 kilovolt. After that low tension, we have high tension cables, high tension cables, HT cables. So these are from 1 kilovolt to up to 11 kilovolt. 1 to 11 kilovolt. After that we have super tension. We have super tension cables, EST. These are 11 to 33 kilovolt. 11 to 33 kilovolt. They are asking 33 to 66. That will be extra high tension. Extra high tension. Extra high tension. Call it as EHT. EHT. 33 to 66 kilovolt. Okay. And after this we have extra super tension also. Extra super tension. Okay. EST. EST. This will be from 66 kilovolt and above. 66 kilovolts and up. So generally we are going to take up to 132 kilovolt. This is the maximum transmission voltage in underground cables. Okay, so here 33 to 66 is nothing but extra high tension. So the answer is option D. The classification is very important, so try to note down. Coming to the next question, which of the following is not a property of good insulating material used for cables? Not a good property. So insulating material must be high resistance, must be high dielectric strength, must be non-inflammable. Okay, and permittivity is not a thing. Okay, so it must having some less permittivity, then only it may not allows the charge through it. Okay, so it is not a property of good insulating material. Okay, the ratio of line to line capacitance and line to neutral capacitance is dash. Line to line. So here we have already discussed the same concept in the overhead lines. So in that also the capacitance between line to neutral, capacitance between line to neutral is equal to 2 times of the capacitance between two lines, between the line to line. So here also the same concept, they are asking line to line and line to neutral. So send this one to that side, line to line by line to neutral is equal to 1 by 2. So 1 by 2 means, so answer is option C. 1 by 2, so the answer is option C. Okay, all of you clear? Coming to the next question. The capacitance measured between the two cores of a 3-core cable with a sheath earthed is 3 millifarad. The capacitance per phase will be dash. Capacitance per phase. Per phase means between line to neutral, correct, is equal to 2 times of the between the two lines. Between the two lines. Between the two lines are two cores. They have given 3 millifarad in the sense. 2 into 3 millifarad, that is equal to 6 millifarad. So the answer is option C. 6 millifarad. So the answer is option C. Okay, all of you clear? Coming to the next question. The material commonly used for sheath of underground cable. Commonly used for sheath of the underground cable. Generally, for sheath of the underground cable, we can use lead or aluminium. Lead or aluminium is going to be used. Okay, generally lead or aluminium is used. So here lead given na, so we need to go with the lead. Okay, coming to the next question. In an insulated cable having core diameter is D, overall diameter is D. So if it is a core, that is like conductor, this diameter is small d. Let us take somewhat of big to understand. This is considered as core, a small d, and upon that we have the insulation. So this is the overall diameter. Overall diameter they have given capital D. Then the ratio of maximum to minimum dielectric stress is dash. Maximum to minimum dielectric stress is dash. Okay, so let us take maximum dielectric stress, G max. G is equal to V by D na, so V by D ln of capital D by small d. Okay, that is overall diameter by core diameter. If you can consider minimum dielectric stress, G minimum is equal to V by overall diameter capital D ln of capital D by small d. So they are asking maximum to minimum na, maximum to minimum ratio. So maximum V by small d ln of D by small d by V by capital D ln of capital D by small d. Okay. So more dielectric stress and for the core. So that's why I have taken small d here, and here minimum dielectric strength. So you can consider the total or overall diameter. So if you cancel out these two, okay, this one, then you will get capital D by small d. Capital D by small d, that is overall diameter by core diameter. Overall diameter by core diameter. Capital D by small d. Okay, coming to the next question. If the insulation resistance of 2 meter length is 10 mega ohms, then 8 meter long sample having what is the having the insulation resistance of dash. We know very well insulation resistance is always inversely proportional to the length. Inversely proportional to the length. Why? Because here if it is the core, upon that we have the insulation like this. Okay, this is the total insulation. So that means as the length of the core increases, insulation also increases like this between the core and insulating material. The insulation resistance is like this. That means resistances are added in parallel. So as length increases, the resistances are added in parallel means resistance is decreases. So inversely proportional. Inversely proportional. So for 2 meters it is the 10 means, for 8 meter it is increases 4 times means resistance decreases by 4 times. So that is 2.5 mega ohms. So the answer is option C. Okay. So try to remember insulation resistance is inversely proportional with the length. Inversely proportional with the length. Actual formula for the cable insulation resistance is equal to rho by 2 pi L log R2 by R1 or capital D by small d. Okay, capital D by small d. From this one, insulation resistance is inversely proportional with the length. Okay, from that formula also we can get idea, or just by understanding also we can get the idea. Okay, so whenever they are asking insulation resistance, that is inversely proportional with the length. Coming to the next one, the bedding of a cable consists of dash. So the bedding is used for to reduce the mechanical stress. Okay, stress on the core. So for reducing, we are going to use the smooth material. Okay, that is jute or Hessian cloth. Jute or Hessian cloth. So the answer is option C. Dielectric loss is proportional to dash. Dielectric loss is proportional to dash. So dielectric loss D is equal to V square omega C tan delta. Okay, so that is dielectric loss proportional to omega. That is omega is nothing but 2 pi f na. So dielectric loss is directly proportional to frequency. Directly proportional to frequency. So the answer is option C. Okay, answer is option C. Coming to the next one. The insulation resistance of a single core, the insulation cable is 200 mega ohms per kilometer. For 5 kilometer is dash. So they have given for 1 kilometer it is 200 mega ohms. For 5 kilometer it is dash. We know very well insulation resistance is inversely proportional with length na. So length increases 5 times. So then resistance decreases by 5 times now, 200 by 5, that is equal to 40 mega ohms. Okay, as length increases, insulation resistance is going to be decreases. Okay, so the answer is 40 mega ohms. Coming to the next question. Next question. A cable has inductance of 0.22 millihenry per kilometer and capacitance of 0.202 microfarad per kilometer. What is the surge impedance of the cable? Surge impedance of the cable. So surge impedance ZS or characteristics impedance is nothing but root L by C na, root L by C, 0.22 milli by 0.202 micro. Okay, 0.202 micro. So make it as 2.2 into 10 power minus 2 by here also 2.02 10 power minus 6 will come, minus 5 will come, minus 5. So almost to minus 5. So let us take almost 2 as cancelled. Approximate I am going. Okay. So then 10 power minus 2, 10 power minus 5, 10 power minus 3 will becomes 10 power 3. That is root 1000. Root 1000 in the sense 30 something na, maybe 30 something. So the answer is option C, I think 33. So you will get 33. Okay, root 1000 in the sense 30 square means 900. 33 squares may be approximately 1000. So we can easily go with the 33. Okay, coming to the next question. The dielectric loss in the insulation of lossy underground cable due to leakage current is dash. I have already given the formula for this. Okay, so it is very easy question. You know what is the dielectric loss? V square omega C tan delta. V square omega C tan delta. So the answer is option B. So the answer is option B. Okay. Coming to the next question. The metallic sheath is usually made up of lead or aluminum. I have already given lead or aluminum. Okay. So this is the cross-section diagram of underground cable. So here we have the conductors. Here we have the conductor, that is core copper cable. Okay. So upon that maybe paper insulation we are going to use. Okay. So to avoid that, that means to get the insulation between the cores, we are going to use generally the paper insulation. Okay, upon that paper insulation, we are lead sheath, metallic sheath, metallic sheath. Okay, so here we can use lead or aluminum, lead or aluminum. Okay, so what is the purpose of this metallic insulation or metallic sheath? To protect air from, to protect a core from moisture, moisture and any gas and any acid type alkalines or gases, whatever it may be. Okay, after that we are going to use bedding to reduce the mechanical stress. So jute or hessian cloth. Okay, and then armoring. So generally we are going to use the steel armoring. Okay, steel armoring to get the mechanical protection for all these parts, mechanical protection for all these parts. Okay, so here in this way we are going to construct the underground cable. So here metallic sheath, lead or aluminum. Lead sheath are used in cables to dash. Why we are going to use the lead sheath? To increase the moisture, to the moisture from the atmosphere. So that means to prevent ingress of moisture, to prevent ingress of moisture. Okay, so it avoids the contact of any moisture, alkalines or acids or gases, whatever it may be. Okay, next question, a very important one. If r is the radius of a core, small r is radius of the core, capital R is the sheath, radius of sheath cable, capital R, and the cable operates stably from the viewpoint of dielectric strength is dash, from the viewpoint of dielectric strength is dash. Generally capital R must be greater than small r, correct? Capital R must be greater than small r, so total diameter always will be higher. Okay, so if it is in this case, if it is in this case, small r by capital R, small r by capital R must be less than 1. Okay, small r by capital R must be greater than 1. Correct? In denominator higher means always we will get the less than 1. So we have one particular is there. So small r by capital R is at least less than 0.368. If it is a factor, then we can get a very good dielectric strength. So the answer is option D. Generally, we have the rule small r by capital R must be less than that of 1 by E. What is this E? E is a factor and we have the E value is 2.7. Okay, so at least this much of factor is there. Okay, so if it is small r by capital R is less than 1 by 2.719. Okay, so then small r by capital R 1 by 2.7 means 0.368, 0.368. Okay, so from this one we can get idea capital R must be greater or equal to 2.7 times of the small r. This is the general idea. At least it is a 3 factor. Okay, 3 times of the core diameter. Okay, for example, if the core diameter is 3 centimeter, capital R must be at least 9 centimeter. So if it is a total cable diameter, then it is having very high mechanical strength. Okay, so this is the thing. If you know this thing, from this one we can get idea small r by capital R is less than 1 by 2.7. So that is small r by capital R is less than 0.368. So the answer is option D. Okay, so the answer is option D. So finally what we can say, the core diameter is somewhat of less always, the total diameter must be very high. Okay, coming to the next one, the charging reactance of 50 kilometer length of line is 1500 ohms The charging reactance for 100 kilometer length of the line will be dash. Okay, so charging reactance Xc is equal to 1 by omega C. Okay, and we know very well capacitance is proportional to length. So Xc is equal to 1 by omega, as C is proportional to length in the sense Xc is inversely proportional with the length. Okay, Xc is inversely proportional with the length. So in this case, for 50 kilometer, they have given 1500 ohms. For 100 kilometer, that is, it is increases by 2 times, means inversely proportional means decreases by 2 times. That is equal to 750 ohms. So the answer is option C. So answer is option C. All of you clear? Xc is equal to 1 by omega C, that is capacitance is proportional to length, means Xc is inversely proportional with length. Okay. And coming to the next one, a cable has following characteristics: L is equal to 2 Henry per meter, capacitance 2 Farad per meter. The velocity of wave propagation through the cable is dash. We know velocity of wave propagation V is equal to 1 by root LC. 1 by root LC. 1 by root L is 2, and this is also 2 given. So 1 by 2, that is equal to 0.5 meter per second. 0.5 meter per second. Very important formula. The velocity of wave propagation through the cable is 1 by root LC. Okay. If they have given relative permittivity ER, then velocity V is equal to 3 into 10 power 8 root 1 by epsilon R. Root 1 by epsilon R. This is the formula if they have given relative permittivity. Okay. Coming to the next question. Yes, here they have given the velocity of traveling wave through the cable at relative permittivity 9 is dash. For this, if they have given ER, then V is equal to 3 into 10 power 8 root 1 by epsilon R. 3 into 10 power 8 root 1 by epsilon R is 9. So 3 into 10 power 8 into 1 by 3. So that is equal to 10 power 8. So 10 power 8. So the answer is option C. This type of questions are very repeated, very important for all JEE and AE examinations. Okay. Very, very important, guys. So the answer is option C. Coming to the next one, the most commonly used material for insulators. Now we are going to practice the questions belongs to insulators of OH lines. Okay, overhead lines. Most common material is nothing but porcelain. Porcelain is used as the most common material. And for 11 kilovolt system, the insulators used at a dead end and sharp curves. In case of dead end and sharp curves, we can go with two types. One is a Shackle type, okay, and second one is a strain type. We can also call it as disc type. Okay, so the Shackle type is generally preferred whenever the voltages are less than 33 kilovolt. So especially whenever the voltage is 11 kilovolt, we go with the Shackle type. Okay, we can go with the Shackle type. So because of less maintenance, okay, it can provide very high mechanical strength at the dead ends or sharp curves or railway crossing or whatever it may be. Whenever we are going to take the voltages are greater than 33 kilovolts, then these are not preferred. Okay, so in this case we are going with strain type. We are going to use the strain type. Okay, so from this one we can get the idea 11 kilovolts is generally you can say distribution voltage. Voltages are less than 33 kilovolt. In that case we go with the Shackle type. If they have given voltages greater than 33 kilovolt, then you can go with the strain type. Okay, don't confuse in this one. So that's why this type of question is very, very important for exams. Pin insulators are normally used for voltage up to 33 kilovolt only. If the voltage is greater than 33 kilovolt, then the cost will be proportional to V power X. X may be more than 2. Okay, so that means cost will be increases a lot. So that's why we may not go with more than 33 kilovolt. Okay. If there is a more than 33 kilovolt, we can go with Disk type. Disk type. Which of the following insulators are used for 132 kilovolt? 132 kilovolt disk type we may go with. Okay, disk type are using. The insulators may fail due to any of the above, maybe flashover, maybe short circuit, maybe deposit of dust. So you can say any of the above. And the ratio of puncture voltage to flashover voltage. Puncture voltage to flashover voltage is nothing but you can say safety factor. Na? Safety factor is equal to puncture voltage by flashover voltage. It is always greater than 1. Generally, the safety factor is we maintain 10 to 12. Why? Because the puncture voltage must be greater than the flashover. We maintain like that. So it must be greater than 1 in the sense. So the answer is option D. Answer is option D. Okay. The long transmission line insulators used at a dead end are sharp curves. So in case of long transmission lines, in the sense voltages are always greater than 33 kilovolts, very high voltages. So in the high voltages, we go with the strain type. Okay. So if the voltage is less than 33 kilovolt, so then we can go with the Shakil. Okay, here our advantage is nothing but they have given any Shakil type here. So directly you can take the answer as strain. Okay, no need of confusion. The voltage across the various discs of string of suspension insulator having identical disc is different due to dash. Why the voltage across the various discs is different? Because of mutual capacitance. That is also nothing but you can say shunt capacitances. Okay, that is nothing but due to shunt capacitances. How the voltage distribution? For example, here, if it is the pole, okay, from the pole we have the cross arm. Okay, and here we have our conductor. This is our conductor. Okay, for example, if we have the 4-disc insulator, 2 disc, 1 disc will be represented as capacitor. Okay, so now there is a self capacitance will be exist between the disc. Okay, so this is the conductor, this is the disc. Okay, so here between the pole and this conductor also may be having some mutual capacitance is formed. Okay, so let us take it as the C dash. Here also C dash. Here also C dash. Okay, so here from this one we can say the current distribution. If it is the I1 current, okay, it is the I2, it is the I3, it is the I4, and voltage across the first disc is considered as V1, it is V2, it is V3, it is V4. Okay, it is V4. Now coming to the first one, if you concentrate on this point, if you apply the KCL here, I2 is equal to I1 plus some amount of the current is also flowing through this one. Now let us take it is I1 dash, I1 plus I1 dash. So current here we have the voltage and capacitance. Okay, whenever we have the voltage and capacitance, voltage is equal to I into Z. Okay, I into Z. So here Z is nothing but here capacitive reactance. Xc is nothing but 1 by omega c. So I is equal to V into omega c. So here from that one, I2 is nothing but V2 omega c. I1 is nothing but V1 omega c plus I1 dash. Here V1 omega c dash. Okay, I1 is nothing but here the capacitance C dash is there, na? C dash. So from this one we can get V2 is equal to, if you cancel out omega, V1, C is cancelled out. Here C dash by C. Let us take K is the factor. Consider as C dash by C. Then V2 is equal to V1 plus V1 into K. So V2 is equal to V1 into 1 plus K. Okay. So in the same way, let us take V3. V3 is equal to V1 into 1 plus 3K plus K square. The same way V4 is equal to V3 plus V1 plus V2 plus V3 into K. Okay, so we have these voltages. That means from this one, what you can say, V4 is somewhat of higher. So this is the higher. This voltage is lower. So we can get the idea, voltage near to conductor is higher, near to cross arm or farer from conductor is lower. Okay, so those 2 points are very important. So we are having different voltages. Why? Because of this K. Because of this K, we are getting different voltages. Whenever the K is 0, if the K is equal to 0, then V2 is equal to V1, V3 is equal to V1, V4 is equal to V3. That means V1 is equal to V2 is equal to V3 is equal to V4. So whenever K is equal to 0, we may get all the voltages are equal. When it will be happen? Whenever C dash is equal to 0. So whenever this mutual capacitance is 0, we may get all the voltages are equal. We can get 100% efficiency. But here the C dash is not 0. That's why we are getting different voltages. Correct? So the voltage across the various string of suspension is different due to this K factor, that is due to C dash. That is C dash is nothing but mutual capacitance or capacitance between pole to insulator disc. Okay, this pole is connected to ground, so that's why you can say, take it as a shunt capacitance to the ground. Okay, all of you clear? And here the very important point is voltage near to the disc is higher, voltage farther from the conductor is lower. Okay, so use of suspension type insulator, the string efficiency can be improved by. So if you want to improve the string efficiency, we can use the longer cross arm. Yes. So here K is equal to C dash by C. If you reduce the C, then K is reduces. If the K is reduces, voltage may be somewhat of equal. So efficiency will be increases. So how we can decrease the C dash? If you maintain the long cross arm, then the distance between these two is more. As distance is more, C is equal to epsilon A by D. As distance is more, we can reduce the C. Okay, as reduce the capacitance, K is reduced, so efficiency will be increases. Using guard ring, so we can go with guard ring also. So if you use the guard ring, so guard ring is like this. If you have mutual capacitance C dash, the counter capacitance is formed here. Okay, this counter capacitance is formed here. This will be cancelled out. So we can reduce the C dash. If we reduce the C dash, K will be reduces, efficiency will be improves. So it is a practical method. And grading of insulator disc. If we maintain different capacitances, then also we can get the equal amount of voltages. Whenever we get the equal amount of voltages, then also efficiency will be improved. So 1, 2, 3. So the answer is option A. Okay. By reducing the cross arm length, we can decrease the efficiency, not efficiency will be increases. Okay. So the answer is option A. Coming to the next one, the number of discs in a string of 400 kilovolt AC overhead lines in the range of. So let us take 400 kilovolts is the line. So for phase, if you can consider by root 3 by 11. So at least you can maintain 1 or 2 extra. Okay. So then you will get 22 to 23. So the answer is option C. The number of discs required for 400 kilovolt is 22 to 23. Coming to the next one. In the 3-unit insulated disc, voltage across the lowest disc. Pole, cross arm, 1 disc, 2 disc, 3 disc. What they have given? Voltage across the lowest. V3 is equal to 17.5 kilovolt. And string efficiency given as 84.28. The total voltage across the string will be. What is the total voltage across the string? We have the formula. String efficiency is equal to voltage across total string by number of discs into voltage of disc near to conductor. Near to conductor. Okay, near to conductor. If you want total voltage V, string efficiency 0.8428 into number of disc 3. Voltage of disc near to conductor 17.5. So if you calculate this one, we will get approximately 17.3 is 50, 50 into 8 40, 40 something. So 40 something means 44.24 or 25 kilovolt. So the answer is option C. Okay. So string efficiency formula very important. Voltage across the total string by number of discs. N is the number of discs into voltage of disc near to the conductor. Voltage of disc near to the conductor. Okay. If, for example, from this one we can get the idea. If voltages are equal, what we will get? So let us take V1 plus V2 plus V3 total voltage by number of discs into voltage near to the disc is V3. If all are equal, then what you will get? V1 is equal to V2 is equal to V3. Then it is a 3V3 by 3V3. So you will get 1 that is equal to 100% efficiency. Okay, so that's why whenever the voltages are equal, we may get 100% efficiency. That's why we need to reduce the K value. We need to reduce the C dash value. Okay, coming to the next one. Two insulator discs of identical capacitance value C make up a string of 22 kilovolt 50 hertz single phase overhead line insulation system. If the pin to earth capacitance also C, the string efficiency is dash. Here they have given two insulator discs having capacitance C. Okay, and the capacitance pin to earth. This capacitance also C given. Then what about the string efficiency given? So string efficiency is equal to total voltage across the string V1, V2, V1 plus V2 by number of disc into voltage near to the disc. This is the formula, correct? So here what is the K? K is equal to C dash by C. Here C dash is also a C given, C by C, that is equal to K is equal to 1. Okay, we know very well V2 is equal to V1 into 1 plus K na? V1 into 1 plus K. So V1 into 1 plus 1, that is equal to 2V1. So V2 is equal to 2V1 in the sense V1 plus 2V1 by 2 into V2 is equal to 2V1. So 3V1 by 4V1. So V1, V1 cancel. 3 by 4 means 0.75. So that is 75%. 75%. Okay, all of you clear? V2 is equal to V1 into 1 plus K. So V2 we will get 2V1. So that is 75% we will get. Okay. So if we know the efficiency formula and V2, V3, V4 formulas, it is very easy. If you forget this, then you can calculate by using the formula like this. Okay. If the frequency of transmission system is changed from 50 Hz to 100 Hz, the string efficiency will be dash. Here, the string efficiency depends on voltages. So here it is not dependent on frequency. So remain unchanged. Okay. So if the frequency changes, both C dash and C both changes. So again K will be same. So string efficiency may not depend upon the frequency. Okay. Stringing chart is useful for dash. It is useful for finding the sag in the conductor. Okay, not stringing that is not string voltages or not string efficiency. Okay, it's not for designing of insulator string. It is used for finding the sag. Okay, it will give the relation between sag, tension, and span length. Gives tension, sag, sorry, tension, sag, temperature. That is the curve formed between this. Okay. And for an existing AC system, the line, the string efficiency is 80%. Now, if the DC voltage is applied with the same setup, what about the string efficiency? If we go with the DC, then capacitance effective. There is no mutual capacitance effect. So whenever the capacitance effect is zero, then K value is almost zero. As K value is almost zero, then V1 is equal to V2 is equal to V3 like that. Whenever voltages are equal, then what about the string efficiency? Total V1 plus V2 plus V3 by the number of discs. Then generally, example I am taking 3 discs. Okay, then 3v3. So all are equal means 3v3 by 3v3. So you will get 100%. So it is 100% we will get. The string efficiency may be 100%. Okay, coming to the next question. A string insulator has 4 units. The voltage across the bottommost means V4. The string efficiency. Okay, string efficiency is nothing but total voltage by number of discs into near to the disk. Okay, so here V4 is given 0.33 of total voltage. So let us take that one, Vt by 4 into 0.33 of the Vt. So it is cancelled out. Okay, so 4 into 3, that is 1.2. 1 by 1.2 means very near, less than that of 100%. So you will get approximately 75%. So the answer is option B. Okay, or 0.33 means 1 by 3. 1 by 3 means it will goes to the numerator 3 by 4. 3 by 4 means 75%. Okay, so the answer is option D. So like that we can go with. Okay, so once again note down this formula. Voltage across total string by number of discs into voltage across near to conductor. Okay, near to conductor. Yes, from that formula you can easily calculate. Yes, the next questions are belongs to protection. So this protection based questions we will discuss in the next session. Okay, and students, if you want download the PDF, you can visit sunilengineeringacademy.com. In that you will get 1 minute video, that is how to download the PDF. That is the first slide. In the first slide only you will have how to download the PDF. If you watch that 1 minute video, then you will get the idea how to download the PDF. Okay, so all of you try to visit and try to download the PDF for quick revision. Okay. So I'm going to show you. So if you open sunelengineeringacademy.com, here how first video how to download the PDF. Okay, if you watch this one, you will get the idea how to download the PDF. You will get all the 6 electrical subjects or individual subject. If you go with electrical engineering PDF, all 6 subjects, each and every PDF. Okay, basic electronics, circuit analysis, only MCQs, circuit machines, full nodes, machines, MCQs, power systems, nodes, power systems, MCQs, measurements, nodes, measurement, MCQs, utilization. Okay, so you will get individual and you will get total. Okay, so you can download from this. Okay, students, we will discuss the remaining, that is protection based questions, in the next session. All of you, thank you so much for watching. Take care. Bye, guys.